Hi everybody, welcome to Test 3 review in Calculus 2. Just like last time, I will not put the face cam on the screen so we can have as much information as possible on the screen. Alright, just go straight to the first one. On the first one, we'll use comparison test. To see that if this sequence is convergent or divergent. Right. So we use the comparison test or limit comparison test. Either way. So when this type problem, when we see usually a ratio or something similar to it, so we will take the term with the highest power on the top and then highest power at the bottom. More specifically, we consider this ranking, and here we have the k to the 9, which is this. P is a constant, so we have that one is going to be bigger than a constant, so we're going to have 1 over 3 over k to the 9. So in this case, we'll compare to the series, and let's say if this term is 1 over 3k to the 9 plus 1, then the bk, we will take the one with the highest power on the top, highest power at the bottom, or the one with the highest ranking on the top and the one with the highest ranking at the bottom. So we just have 1 over 3k to the 9 power. Right. Now, certainly we can compare to this, or we can also compare to the one without the 3. Let's see what we have here. So those are the options. And I'm going to use this one because once we have that, the coefficient does not affect much, so just do the one without the coefficient. So we compare with that, the series of this term. Right. Now, so if we let bk equal to that, then we have the series of bk and we have that, and this is a p series where p equal to 9. Now if p is equal to 9 for p series, by the way, the convergent on the test is on the bottom right. So we look at p series, bigger than 1, it will be convergence, less than or equal to 1, divergence. So this is greater than 1, so b sub k is convergent. So this b sub k is convergent. Now if b sub k is convergent and we compare a series of a sub k and b sub k, so a sub k is also convergent. Right, so we have that. Now, before we go to the next problem, actually, here's one thing we need to do for the comparison test or limit comparison test. For limit comparison test, we actually need to find the limit and make sure that it goes to a constant. It goes to a finite number. So, limit comparison test is this. We actually need to show that the limit It's a finite number. So let me just put that here. Technically, the limit comparison test need to show that cannot be less than or equal to, have to be less than infinity. So it is a finite number. Right. So and we show that rather quickly. H of k is that. And B of k is this. Multiply reciprocal. Yeah, so you have k to the 9, k to the 9. On the top, the highest power, k to the 9. And we'll take the highest power on the top. And highest power at the bottom. And highest power at the bottom, we don't need the 1 here. So divide that, we have 1 over 3. And suddenly, it is between 0 and infinity. Right, so technically, this is a complete problem. However, on the question on the test, or question like this, we don't need to show this part. As long as we take the one with the highest ranking on the top, with the one with the highest ranking at the bottom, if we keep those two terms, then we don't need to show this. Once again, take the one with the highest ranking on the top, and keep the one with the highest ranking at the bottom. If we keep those two terms, we don't need to do this. Right. Next is similar to it. Limit comparison test. Even though the first one say comparison test, so actually we compare that and we say for comparison test we actually say h of k is less than b of k, but like that. I just use the limit comparison test. It's a lot more versatile. Use limit comparison test. Have k to the 4th plus 4 and k to the 5th plus 7. Right. So in this problem, of course, h of k is going to be that term. And in that case, we'll compare to the sequence where b of k, just take the one with the highest ranking on the top, the one with the highest ranking on the bottom, so k to the 4th and k to the 5th. And we'll reduce that to 1 over k. And we're going to compare to this series of that terms. So we have the series b of k which is the series of 1 over k, And by default, we can say this to the first power. And this, once again, is a P series. And P is equal to 1. And of course, we see for the P series, if it is less than or equal to 1, it will be divergent. So this series is divergent. So h of k is also divergent. And we can show this also, but I'm not going to do that here. Yeah. Again, if we take the highest power term on the top, and I should say the highest ranking term on the top, and the highest ranking term at the bottom, and when we simplify, that is the series we compare to. So, 1 over k, and the series diverges. So for a limit comparison test, usually we compare to the P series or a geometric series. Right, number 3. Again, we use either comparison test or limit comparison test. I said I prefer the limit comparison test. Because it have more use than the standard direct comparison test. And so we test for the convergence of this series. Right. So in this case, let h of k be the term. It's okay, it's a term, so there's no summation. And then we will compare to b sub k. Take the highest ranking term on the top, because there's just one. The highest ranking at the bottom, of course, 5 to the k. But what is actually that on the list? So k or n, it doesn't matter. In here, 5 to the k. 5 is a constant, k is the index. So actually, b to the k is here. And compared to the previous one, we have, for example, k to the 5th. K to the 5th is this one, and 5 to the k. Let me write this down. What I actually mean is, we have 5 to the k, and that is going to be bigger than k to the 5th. So exponential is going to be bigger than power. So even though if we have h of k, let's say if we have k to the 5th, we still ignore that, because 5 to the k power rank higher than k to the 5th. Onto this list, the one where the index on the exponent is higher than the one with the index at the base. Right, so that one is greater than k to the 5th. Regardless, we just compare to that. Right. Now we will look at the series of b sub k. and base of k 1 over 5 to the k power. By default, we can always say 1 raised to any power, still 1. So we can put both of them inside k. And this one is a geometric series. For geometric series, and r equal to 1/5. And because r is between -1 and 1, so geometric series, if absolute values of r less than 1, convergent, greater than or equal to 1, divergence. Since absolute values of r less than 1, because of that, the series bk convergent. And since we compare these two, a sub k is also convergent. So the original is convergent. Right. We compare test with that and show that the series is convergent. And that is the limit comparison test. So how do I do this? Actually, the option is D. It's not shown on the screen. Let me do this real quick. So where did we? I can change the text color to that better. Really don't need that. Right, so it's good. So here we can choose limit comparison test. We don't have any option. So we can only compare to that, and it show that converge. So it's still A. Sorry. Yeah. So either limit comparison test or comparison test, we use compare to this geometric series and it's convergent. I don't really like the question, kind of limited our choice. Right. For limit comparison test, I prefer this test on paper, but cannot really do that. Right. So that So ace of k being that and now we'll compare to so we'll take the highest ranking on the top and highest ranking at the bottom. At the bottom we have k and 3. The k has a higher ranking than 3. That polynomial is higher than a constant, obviously. Because k goes to infinity, k plus 3 or not, have the plus 3 or not doesn't really matter. And in that case, we extended 5k and k to the 1/2 for square root, and we're going to have 5 over k to the 3/2. And once again, if this is 5 or any constant, we can just choose 1 instead. So let's see, what option do we have? Right, a lot. But that is the choice. Or we just say 1 over k to the 3/2. Yeah. If the numbers not really matters, what I mean is this: we can have 5 multiplied to 1 over k to the 3/2. The constant multipliers here we can ignore, and we'll just take this part to be piece of k. And how about what's that? K equal to 1 to infinity of piece of k and this is a p series. Where p is equal to 3/2, and according to the p series, it's on the bottom right. This is bigger than 1, so it will be convergent. So the series piece of k is convergent or converges, and piece of k is convergent, so it's ace of k. So that is the limit comparison test when we compare piece of k converges, so it's ace of k. Another limit comparison test. By the way, let me move this somewhere else. Because when I move my hand, I kind of got a weird feeling about it. Anyway, number 5. Use the limit comparison test. And I'm going to test this series. Square root of n. By the way, if you see this kind of problem on the test 3 is fine, but if you see this kind of problem on the final, I guarantee that you have to show work for this kind of problem. You cannot just say converge or diverge. Right, but first let ace of k be that term. I will write n to the 1/2 instead of square root of n. And the bottom 10n to the 3/2 plus 7n minus 4. And what we compare to is we compare with the highest ranking on the top and the highest ranking at the bottom. So we compare to b's of k. Take the highest ranking on the top, highest ranking on the bottom. So that's what we have, pretty much. So 3 to n to the 1/2, 10 n to the 3/2. So we have 3 over 10. The n to the 3/2 and the n to 1/2 cancel out. We say is n. One half minus 3/2 is minus 1. So we move to the bottom. Right? 1/2 minus 3/2 is n to negative 1. Move to the bottom becomes 1 over n. And what we compare to is compared to this. That is b's of k. So b's of k is 1. There's no k here, there's n. Sorry. So b's of n is 1 over n. And if we take the series of b's of n equal to 1 to infinity, and by default that is to the first power. So this is a p series. And p series and n equal to 1. I mean p is equal to 1. So p is equal to 1. So b's of k is divergent. Or that in verb is that. So that is divergent. And if b's of k is divergent, so is a. Just keep doing that. B's of n is divergent. And we compare the two. So a of k or a of n is divergent too. Yeah. So take the highest ranking on the top and the highest ranking at the bottom. And then when we divide and simplify, if there's a constant, don't really need that constant multipliers. And then at the end, whatever b's of n is, if it is convergent, the whole thing is convergent. If it's divergent, the whole thing divergent. Right, so those are the limit comparison tests. Like I said, most of them we just I use the limit comparison test. And technically, we need to show that part too, but like I said, take the one with the highest ranking on the top and the one with the highest ranking on the bottom. In that case, both of them converge or both of them will diverge. Right. Next one we have, by the look of the negative 1 to the k, this is definitely alternating series for sure. And what's this one? Number 6. determine if the series convergent or diverge. So we just have this series. Okay. When we see -1 raised to a power, the power that we change from positive to negative, that definitely is going to be alternating series. When we see -1 raised to the power, whatever that power is, it's changing from positive to negative. A little bit darker. Okay, better. So in that case, ignore that term. The rest is a sub k. Right, alternating series test. What do we have? Right, so I'm just going to write that instead. So alternating series, we're going to check two boxes. Check to make sure it works. First is a sub k non-increasing. And the second box is what is the limit when k goes to infinity of a sub k. Is that equal to 0? So we're going to check to see if both of these criteria are satisfied or not. So the first one, when we look at 4 over k to the 9 plus 4. Now, when k getting bigger, the bottom getting bigger. If the bottom getting bigger, where the top stay constant, the quotient getting smaller, right? So let's summarize as follows. As k increases, k squared plus 4 as a whole is also increases, right? So since the denominator is increasing, the top is constant, the ratio decreases. The reason being bottom increases. The bottom is increasing, but the top is constant. So we have the same number, but we keep divide by a bigger and bigger number. And this of course gives us the quotient is decreasing. We have a finite number, but we just keep divide by a bigger and bigger number. So the quotient is getting smaller and smaller. So yes, if it is decreasing, then it is non-increasing. So that's good. Second, we check what is the limit as k goes to infinity. For something this obvious, we can just do that. If it is more confusing, then we actually have to take derivative, because derivative is negative equivalent to the function is decreasing. Anyway, so we take the limit. As k goes to infinity, take the highest ranking on the top and the highest ranking at the bottom, and then put in infinity to the 9. And so we have finite over infinity, which is equal to 0. Yeah, so that check as well. So since both of this box are check, both of these conditions are satisfied, so we say the series is convergent. If one of them fails, the series diverges. Right. So h of k is equal to, as non-increasing as k index. So it have to be non-increasing. Non-decreasing doesn't work. So this works for every value of k. Either that right. Oh, I hate this. Oh, so we actually can do that. So we scroll down, evaluate the limit, and we know the limit it go to 0, right? So those two criteria are satisfied, and so the series converge. Right. Number 7. Determine whether the following series converge. Once again, we have this. That is alternating series. And ignore that, we have h of k. Right. By the way, we don't have to do much. This one fails. As k go to infinity, h of k equal to 1. So the series diverge, for sure. But for some reason that my MATLAB will actually have to check the first condition. Right, we do that anyway. So is h of k non-increasing? Second box, what is the limit? Is that equal to 0? We know for sure that when we check the limit for k go to infinity, highest power on the top, highest power at the bottom, k squared over k squared is 1. So the limit equal to 1. So we know that this one fails and the series diverges already. But for some weird reason, my MATLAB asks us we have to do that. Oh, there's an option here. It says it is diverged because the limit, yeah, look like this is working here. But let's just check. Right. What happened for that? I said kind of difficult to compare because the top is changing, the bottom is changing. So we don't know if the quotient decreasing or increasing or whatever. So again, if the bottom is increasing, the top is constant, it's easy to say. This one, both of them is changing, both of them is increasing. We cannot really tell. What we can do is, let's say if that is the case, let the function be something similar to that. So consider to this function. And then if we take derivative, this is a quotient rule, derivative of the top, the bottom, minus the top, derivative of the bottom. Square. Right. So multiply it out to x cubed plus ax and x squared times 2x minus 2x cubed minus so plus 4x that ax plus 4x. So we have 2x cubed cancel out, ax and 4x, that's 12x. Now what we have is for this one, k is equal to 2 to infinity, so certainly k is positive, right? Now if k is positive, the top is positive, the bottom or square is always positive, so this one is positive. Now if the derivative is positive, in count 1 it is increasing, right? So actually this one fails as well. So we say the series converges because h of k I think it's going to be this one. H of k is equal to fraction k squared minus 2 over k squared plus 4. Oops. And that is, we show that is increasing, and haven't showed the limit. K squared minus 2, k squared plus 4, take the highest power on the top, highest bottom, cancel out. And that's equal to 1, so that one fails as well. And the limit equal to 1. So both of them fails, it will be divergent. Like I said, one of them fails is good enough, but we have both. I guess that's how they do the watermark. this is, what's numbers? Oh, 8. Right, convergent or divergent. And we have this series. Oh, we said alternating series. Okay. -7 to the n over 5 n to the 5th and 9 to the n. Right, interesting. Once again, we have the negative inside the power of n. That change positive to negative. So this one is alternating series. But we need to modify one bit. We can write that as -1 to the n. Write that. Right. So actually, because of -7, you can write that as -1 times 7 all of which under power of n. So the n power goes to -1 and the n power goes to 7, and that's what we have. And when we see this, that is the alternating series test, because each change is alternate between positive and negative. Right, so obviously what's left is a sub n. Now this will be very difficult to show that using the traditional alternating series test. Now what the reason that is difficult, because if we have to take the derivative of this, that is rather difficult. Right. Now we'll make one tiny subtle change, and that will improve our situation by a lot. Let's look at the ranking. 5 to n to the 5th and 9 to the n, which actually have the higher ranking. Right, so one of them the index at the base, one of them the index on the exponent. The index at the base is significantly less than the index on the exponent. So out of those two, the 9 to the n powers is a lot bigger than this. Now we will make that tiny change and we can improve our situation by a lot. So we have since that is significantly bigger than, we just ignored. So instead, a sub n will be just 7 to the n and 9 to the n. By the way, what the test we're using here actually is the absolute values convergence, implies convergent. So if we compare to that, and of course we can show the toolbox that a sub n is convergent, right? Yeah. So obviously when n increasing, this one is decreasing. And that's clearly check, because this number was less than 1. absolute values less than 1. So when the raised to the power, that one goes to 0 and is decreasing. So let's say we talk about something like 0.5 by square, that's 0.25. So anything that is less than 1 or between -1 and 1 raised to the power, the magnitude gets smaller and smaller. So yes, because of that, it is non-increasing. And it's the limit, it's k. It's the limit at k go to infinity. Oh, that's just we have n in this one. What is the limit of that when n go to 0? When n go to infinity, is that go to 0? And in this case, it does. Once again, because if we have something that is less than 1 raised to the power, think about this. If we have 0.1, for example, raised to the second, 0.01, 0.1 cubed, 0.001, and the higher the power, the closer it gets to 0. And essentially when the power goes to infinity, that goes to 0. So yes, that check, and so that is convergent. However, actually, if I do this problem without using alternating test or anything out of context, the first thing I do is I'm going to just slap the absolute values into it. Absolute values will cancel with the negative, because positive or negative doesn't matter. We just have that. Now, high ranking on the top and highest ranking at the bottom. I'm not going to say that this is E equal to it. This is completely wrong. They are not equal. But what I'm saying is the behavior of the n term will be equal to when k go to infinity. So as k go to infinity, then I will say this term so we take the highest power, the highest ranking on the top and the highest ranking on the bottom. So the term will be equal to when k goes to infinity or when n goes to infinity. And the series not equal to. Right? At n go to infinity, we compare to this. And this converges. Now, since we slap the absolute values into it, so this is converges absolutely. And if it is convergent with an absolute values, it will be convergent without it. So if it converges with absolute values, it will converge without it. And that's the question, the way we should do the problem. And this one also alternating series test. Once again, we see this alternating series. At h of k be 1 over n to 7 over 4. Right. Sorry. On the last problem, if we have, instead of 7, and if this is 10, then the series will be divergent because 10 over 9 is bigger than 1. If a number is bigger than 1 raised to a power, that will go to infinity. The number smaller than 1, it will go to 0. Equal to 1, then it will be 1 because 1 raised to any power is still 1. Right. So that alternating series, I check 2 boxes. Is h of, you know why some problem they have k and some problem they have n? Because I get the problem from 2 different books. Some book they use n and some book they use k. Doesn't really matter those. Non-increasing. And the second box, does the limit equal to 0? So first, that term. Now this one obvious because the top is constant. So if we have the top is constant, the bottom is increasing, the whole thing decreasing. That is the easiest reasoning. So bottom is increasing, the top stays constant. Because of that, the whole thing, the quotient is decreasing. Right, so that is easy reasoning. We have finite amount, but just keep divide by the bigger and bigger number, then the quotient will get smaller and smaller. So yes. And then we'll take the limit as n goes to infinity, h of n. That's some point you can see that's kind of redundant. I mean, I should not say redundant. There's some reasoning along the line. The top is finite, the bottom is infinity. In that case, that is equal to 0. Yeah. By the way, it's wrong to write like this, but we know the limit equal to 0. It's better yet, just don't write anything in the middle and say that equal to 0. Right, so both of the box I check is convergent. Right, the next one, number 10. Right, this one we test for absolute convergent, or just diverge. So we need to check three things. First, absolute convergent, absolutely convergent, conditionally convergent. or divergent. And we have this series which is an alternating series. Right. So, first, absolutely convergent. Just put an absolute values into it. When you put absolute value, because absolute values will kill the alternating. This one positive or negative, positive 1 or negative 1. But with absolute values, it's just 1, right? The bottom though, k is positive. We just have that without the size. So when we put absolute values in, we have equal to that. So we say absolute of negative 1 is the same as absolute values of 1. Just 1. So that's what we have. The top is just 1. Bottom is always positive, so that's always positive. So what kind of series is this? We have k to the 9 over 7. And this is a p series where p is equal to 9 over 7. So what p series says? P series bigger than 1, convergent. And it is convergent with the absolute values, so it will be absolute convergent. And that's all we do, really. So the series converges absolutely because it is convergent with the absolute values. So definitely that option. So just throw in absolute values, see what happens. If it is convergent, that's it. Right. Next, same thing. Absolutely convergent. Conditionally convergent. Or divergent. And we have the series. Right, first thing of course, we're going to put the absolute values in and see what happens. The absolute values, the only thing we'll change is we'll take care of the negative 1 to the k power. We have everything else. K squared, and we have that. I have to be careful with this. And so for that, absolute value will turn the negative 1 to the k power to 1. So we just have that. Now that will be a of k. Right. What is the series that? How do we say if this is convergent or divergent? Now, this will be very simple. What we do is, when we have a little more a bunch of term on the top or a bunch of term on the bottom, it could be useful if we use the comparison test. I mean limit comparison test. But what we compare to is the series when we take the highest ranking on the top and then the highest ranking at the bottom. Right. K square root of k to the 6. We can say k to the 6 to 1/2, which is k squared over 6 and 1/2 is cubed. Reduced is 1 over k. So, what is the series b sub k? B sub k. This series is a p series where p equal to 1, or we call the harmonic series. Which is divergent. It is divergent. So b sub k is divergent. So a sub k is divergent also. Now, all we can say is this is not absolute convergent, because with absolute values it is not convergent. And then we have to do that without the absolute values. Just go ahead and do it. Right. Now this is alternating series, so we're going to ignore that. So we're going to ignore that. And a sub k equal to, without the negative 1, raised to the k power. Right. For this, actually this one, if we use the alternating series test, showing that one is decreasing is kind of difficult. None increasing. And thus the limit go to 0. Actually, to show that is one non-increasing, we have to take derivative, because that kind of that. Yeah, because the top is changing, the bottom is changing. Cannot really say that. If it's increasing or decreasing. But we know for sure the limit though. Let's test the limit first. When we check the limit, because when k go to infinity, we can use the ranking. So this ranking works if it goes to infinity. Has ranking. Has ranking. And we did show that square root of k to the 6 is k cubed. And the bottom goes to infinity, the top is constant. That equal to 0. So that certainly check that box. So is that non-increasing? Well, like I said, we have to take the derivative, and that look complicated. I just look at the graph and see, maybe it helps. Oh, where's the calculator? Forgot, didn't have a calculator yet. Right. Just graph. K square. Let's do the 6. Notice that case from 1 to infinity. I'm going to just zoom out this box. Look like this decreasing. Right, like I said, we have to actually use derivative and show that this is decreasing for some certain values. Right. So let me put the calculator away. Right, so it can be shown that this is, check the box too. I said it's a little more complicated when there's square root and we can take the derivative of this, which I really don't want to do. Right. So if that is the case, then this is conditionally convergent, because both of them check. Like I said, it should be a little less complicated when we have the square root, so don't have to maybe they just give you k to the k cube at the bottom. That would be a lot easier to do. Right. The series converges conditionally because that, no. The series converges conditionally because the series converges without absolute values. But with the absolute value, it diverges, and that's exactly what we have. Right. So we expect to have something similar, I mean, something less complicated than this problem. Because we have to take the derivative of that. It's not impossible, but a little more than what I want to ask for on the test for this particular things. Next we have the ratio test or the root test. So let's look at the few problems. So this one, ratio test or root test. This is ratio test. This is a ratio test. Now this can be done using the root test as well. And so the root test, usually if we have the power of k like this, of the whole thing raised to the k power, that is the root test. But other than that, we can use the ratio test. By the way, on this problem, if we can bring f8 and k under the k as a whole, this one can use the root test as well. But the ratio test is a lot more versatile. We use a lot more than that, not just for this part of the series and the sequence. Right. Right, the root test, where is that? I mean ratio test here. So very easy. We will take, let me zoom in. It is convergent if we have this, and it is divergent if we have that. So we take the ratio of consecutive terms. The next term divided by this term. So first, let a sub k be that. Now the ratio, it is inconclusive when when that ratio equal to 1. So we take the ratio a sub k plus 1 over a sub k. So we put k plus 1 instead of k, negative 6, k plus 1, k plus 1 factorial, and then a sub k, negative 6 to the k, and then k factorial. Divide fraction is multiply reciprocal. Multiply reciprocal. Next, the reason we use the ratio test for this kind of terms, because negative 6 to k plus 1 we can split, factorial definitely we can split. Right, I think I can write everything here. Negative 6 to the k power is negative 6 to the k, and then negative 6 to the first. because when we multiply two things with the same base, we add the exponents. And k plus 1 factorial is k plus 1 times k factorial. Because I just give you one example, like 6 factorial is equal to 6 times 5, 4, 3, 2, 1. And those are 5 factorial. So 6 factorial is 6 times 5 factorial. And in this time we have k plus 1 factorial is k plus 1 times k minus 1, and so back to 1. And all of this at k factorial. So that's why we write like this, k plus 1 times k factorial. Negative 6 to the k power cancel out. K factorial and k factorial cancel out. And so what's left? Negative 6 and k plus 1. Still with absolute values though. Now, so with this absolute values, negative or positive doesn't matter, right? Now, when k go to infinity, the top is finite, the bottom k go to infinity. So finite divided by infinity is 0. And according to the ratio test, if it is less than 1, it is convergent. And convergent absolutely. Yeah, but this one we just say it is convergent. So the test is convergent absolutely because of the ratio test and r equal to 0. Right. Next one is also the ratio test. Right. So first of all, that is a of k. So for the ratio test, usually we have that term, the power, exponent, or factorial. Those come in handy when we use, or even this term can also use the ratio test. Right. So the ratio test, I take the ratio of consecutive terms. Right. First put k plus 1 in for k. K plus 1 for k. And the bottom be just that term. Multiply reciprocal, so we're going to flip it. Again, k plus 1 square cannot really do anything. Just that. But the bottom though, a to the k plus 1, a to the k, a to the first. Cancel that out. We're left with that. Now, k is plus 1 square. By the way, that is positive. That is positive. And that h is positive. We really don't need absolute values if all of them are positive. And for now, just leave that there. Again, we really don't need absolute values because the square is going to be positive. Right. And up from this point, we can just say k plus 1. K has a higher power than 1, so we just ignore the 1 and we go from there. But I just multiply it out. K plus 1 square is k square plus 2k plus 1. And as k go to infinity, highest ranking here, highest ranking here. So I have limit k square cancel out. We have 1 over 8, which is 1 over 8. And 1 over 8 is less than 1 by ratio test. This is convergent, absolutely. So it's convergent absolutely because the ratio is equal to 1 over 8. Right. The next one, actually the root test is a lot more convenient, but they want the ratio test. That's alright. I just realized that this is the recorded video, so I don't have to wait between the end of the problem. I just switch to the next one immediately. You can always pause the video, right? I used to have one long video like this for my lecture class, and I put timestamp for each problem, so you can just click on the timestamp and go to a particular problem. But take like an extra hour to take a lot of time to do the timestamp. It's not that difficult, but I have to, like for every problem, I have to write down what is the time when I finish the problem, and then have to keep track of everything. And So now we really focus on the problem. It's kind of difficult to keep track of everything, and I tend to forget some certain things. Right, ratio test. Ratio of consecutive terms. Right. Yes, after this we need to go back, make one more common. Right, k plus 1 instead of k. Right, and bottom's a to the k. Right. Multiplied reciprocal. Right, now split. This potentially is the problem. Right, a to the k plus 1, a to the k times 8. The bottom, k plus 1 to the k, and then times k plus 1. The top row, k to the k, a to the k. Right, this can cancel. Cannot really cancel anything here. So the top we have 8 k to the k. So what we can do about this though? Let's try this. By the way, they're all positive. So k is positive, so we really drop the absolute values. Right, that's the first thing. Second, both of this term are raised to the k power. So I write that by itself first. K over k plus 1 to the k. And then after that, we have 8 k plus 1. I said I don't know why we have this, but this one is a lot more convenient if we use the ratio, the root test with the k power. Right. Now, when k go to infinity, so this one go to 0, and what this one goes to? No, I just wait for you to think, but actually, no, that already. Note that we have Now let's consider that. And we split so which is equal to that term, and that's of course equal to e. Now all we do is just flip it, so this will be 1 over e, because this is the reciprocal of it. Right, reciprocal of that. And this limit when k go to 0, this equal to 0, so the whole thing equal to 0. So it is ratio test converge because r equal to 0. Right. Now, before we go on further, let's look at this problem real quick. No, just want to look at this. One with the absolute values though will be 6 to the k. So let's just write out. This without the absolute values. So we have 6 to the k. And then k factorial. So according to the ranking, factorial is bigger than factorial is bigger than exponent. So let's go back and do for these two problems. Factorial is a lot bigger than exponent. If we have the bigger number on the top, this tend to go to 0 and the series converge. Because the bottom is way bigger than the top. And this one also converge because a to the k is significantly bigger than k squared. So bigger number on the top, then the whole thing go to 0 very fast, and therefore convergent. Same thing here. The super exponent, I should say, is going to be bigger than that. And if we have the bigger, I should not say higher ranking at the bottom, it will be convergent because that go to 0 extremely fast. Right, next one. 7 to the k and k to the 99. 7 to the k is the exponent, k to 99 is power. So actually this one, the top, has a higher ranking than the bottom. Therefore this one is divergent. But we still need to do it. Let's see if it works that way. And again, ratio test. Even though the 99 seems bigger than 7, but we not compare that. We compare whether whether the index is on the exponent or whether the index is at the base. If the index on the exponent, that will be bigger than the index at the base. Right. So a of k is equal to 7 to the k and k to 99. So r equal to a sub k plus 1 over a sub k So I have 7 to the k plus 1 over k plus 1 to the 99. The bottom 7 to the k to 99. Alright, multiply reciprocal. I don't know why I put R here, but that obviously K. Sorry. Now let's split. Seven to the K times 7 for 7 up K plus 1. The bottom, this cannot really do anything. Cancel that out. Remember, we earlier say that that one is a lot bigger than the bottom, so this one should be divergent. Right. By the way, both of them have the 99 power. So I move both of them inside the power of 99. They're all positive. We really don't need absolute values though. But I just put k plus 1 to the 99 power. Right, when k go to infinity, that one goes to 1. And so pretty much, because k over k plus 1, when k go to infinity, this go to 1. So pretty much we will have 7. And the k plus 1 go to 1 as k go to infinity. So we have 1 times 99 power, which is still 1. 7 times that is 7. Now this is equal to 7. Which is bigger than 1. Which is divergent. Series test diverges because the ratio equal to 7. Right? Right. Like I said, the next one, obviously, because we have the whole thing raised to the k power, so definitely the root test. We can also use the root test on this problem, and definitely we can use the root test for this problem. If we take the root, right, get back to that in a minute. After we do the 16, then we'll go back to 14. This is 16. This is the root test. So the root test is where we take the root row still with the limit when k go to infinity. Where's the root test? Oh, pretty much this. Yeah, so that is the root test. So we take the limit with the root of the k index. And we just have the whole thing there. We need h of k. Not. Just put the whole thing here. Now, the reason, by the way, it doesn't matter. Remember, different here is that in the root test, remember, not only we have that, we have to have the absolute values of h of k. Remember, this is what we need to have. Absolute values of h of k. By the way, since this is positive when k equal to 1 and up, this is positive, so the absolute values are not, doesn't matter. But in the formula, there is the absolute values there. That cancel out. That's convenient, right? We just have 1 over ln of k plus 1. And now if we put in infinity, ln of infinity is still infinity, which gives us 0. If the root is equal to something less than 1, it is convergent. It is convergent because the root test equal to 1. I mean 0. Right. Now go back to 14 real quick. If we take the root of this, if we take the root a to the k, k to the k is equal to 8 to the k to the k. If we take the root test, that cancel out, and we just have 8 over k. As k go to infinity, this one goes to 0. So by the root test, this one is convergent. We don't have to go through all of that. So the root test, when it works, it turned out to be very nice, but very limited application. It had to have the k power there in order to use the root test. Right. With that, we go to 17, which is starting chapter 11 about power series. So we're not going to do the convergent and divergent anymore. We do this is linear approximation. Right, and for this part, I'm going to go to the most important things that we need to know is the Taylor polynomial or the Taylor series. Yeah, there's a formula for linear approximation and quadratic approximation, but ultimately it's going to be this in general. And that also the Taylor series that we do later. Here we have the function is equal to 2x squared plus 5x plus 3, and the center at -4. So linear approximation, linear meaning that the power of 1, right? X to the first, meaning that p1 of x. So we just write that derivative x minus a, second derivative x minus a squared. We're not going to have this term or anything after that, because this one only linear function, so we only have the power of x only, do not have x squared or any higher. So that's how we go, as far as we go. So yeah, that approximation. So what is the values of the function? Well, that's rather simple. The function equal to 2x squared plus 5x plus 3 when x equal to -4, f of -4 equal to -4 store into x, and then we have 2x squared plus 5x plus 3, that's 15, and then derivative 4x plus 5 at x equal to -4, derivative at -4, -16 plus 5, -9, no, 16 plus 5, -11. Right, so we substitute this back in here. Values of the function 15, and then values of derivative this is exactly like the power, the Taylor series that we'll do later. Then x minus a, so we have 15 minus 11 x plus 4, so 15 minus 11 x minus 11 times 4 minus 44, 15 minus 44 minus 29, so negative 11x minus 29. Yeah, so this is the simple form of linear approximation, I mean of the Taylor series, which is including the Taylor approximation, Taylor series, that is. So first find the linear approximation, same thing, and then next quadratic, same thing, but including that, and then use the power polynomial, obtain part A and B, approximate this. Right. So let's do part A, linear approximation. We could do the table like we did with the Taylor series, but this is simple enough. We don't even need the table. Right, linear approximation P1x f of a plus f prime of a x minus a. So the function is 32x to the 3/2. Evaluate at 4. (32) 3/2. Wait, sorry. X is equal to 4. 3/2. 256. How about derivative? Derivative of this, take that to 3/2. Original power minus 1. 3/2 minus 1 is 1/2, which is cancel out 2 and 32. 16 times 3 is 48. We have 632. And at x equal to 4, derivative at 4 is equal to 48 times 4 to the 1/2. Square root of 4 is 2, which is 96. So put it back in the formula. P1 of x equal to the function 256 plus 96 x minus the center. Right, just going to keep this form. Don't need to multiply that out and simplify. Now we evaluate at 4.2. So in this case, x is equal to 4.2. So let's store 4.2 into x. And evaluate this function, 256 plus 96 x minus 4 to 75.2. First, we have 256 plus 96 x minus 4. Right. That's the nice thing about my MATLAB answer. You don't have to simplify. Right. Actually, we'll get back to this number later. Next, quadratic approximation. So that will be P2 right. All we do is we add one more term, second derivative over 2 factorial, and then x minus a square. So we just add one term of the Taylor series, which is, or the Taylor polynomial, which is here. So we're going to have this, and then we add something new to it. So first, the second derivative. Actually, on this one, we should use the table. Second derivative is derivative of this, 48 take down to 1/2, original power minus 1. So which means 24 x to negative 1/2 at x equal to 4. And 4 to negative 1/2. Is 12. So let's write out the formula one more time. P2x f of a plus f prime of a. Yeah, later on we just use the table. Second derivative over 2 factorial. On this one, when we write like this, there's an advantage of writing like this too. 256 function, derivative 96. We know the center at 4, right? A equal to 4. Yeah, in the problem. Second derivative 12. 2 factorial x minus 4 squared. So it will be 256 plus 96 x minus 4. 12 divided by 2 factorial is 6. X minus 4 square. And then later on we put 4.2 into it. Right, so 256 plus 96 x minus 4 plus 6 x minus 4 square. Right? And then evaluate at x equal to 4.2. We store x equal to 4.2 earlier, so we don't have to do that here on the calculator. Already store the values. Now we just enter this function, 256 plus 96 x minus 4 plus 6 x minus 4 square. 275.44. Using linear approximation, we have 275.2. And using quadratic, we have 275.44. Yeah. So notice that linear approximation, quadratic, and then the first term, the first two terms are the same. We're just adding terms into it. That's how the Taylor series are built. Now we're going to use the table. This is number 19. Find the Taylor polynomial order 3, center 0. Notice that in this section they call Taylor polynomial. Later on we'll just say Taylor series. Because the series usually implies that this goes indefinitely, but the polynomial, on the other hand, has finite terms. I just make a table. By the way, let's write the function first. E to negative 2x. You definitely need to know how to do this because you will see this kind of problem on the test 3, and definitely this kind of problem on the final. Because this is the last thing I hope that you forget about this section, is how to do the table for Taylor series. Right. So on this we have k, the index. It goes like that. First we have the k derivative, or the k derivative of the function, and next we evaluate that at the point a. In this problem, a is equal to 0, and later on we know that a Taylor series center 0 is also called Maclaurin series. Yeah, so center 0 is Maclaurin series. Oh shoot. Yeah, the reason I don't like the actual choice because they multiply it out and simplify it with definitely. Anyway, just see, like the function e to negative 2x. Now let's put 0 in for it, and we'll take 1 divided by 0 factorial. Take derivative. Derivative of that is just negative 2 e to negative 2x. That is the chain rule. E to the negative 2x. Doesn't matter what the power is. Derivative is e to the same thing. And it just happened that this is negative 2. So that's why we have this. Negative 2 e to the negative 2 times 0. Negative 2 e to the 0. E to 0 power is 1. So negative 2. Divided by 1 factorial is negative 2. Oh, never. Oh, it's fine. This one center is 0, then we definitely don't need to multiply it out. Much more convenient. Right. Derivative of e to negative 2x is negative 2 e to negative 2x. Multiply it out. 4 e to negative 2 times 0, which is 4. Divide by 2 factorial, positive 2. Third derivative e to negative 2x is the same thing. Eight. E to 0 power is 1. Did I forgot? Yes, forgot the negative. So if you realize that the pattern is 1 times negative 2 times negative 2 times negative 2. So the next one is going to be positive 16, negative 32, positive 64, and just multiply by negative 2 every time. But we have to divide by the factorial. 3 factorial is 6, so negative 4 over 3. Right, so that looks like the last answer, but let's put in the Taylor series, order 3, center at 0. Doesn't matter, let's say the center. F of A, F prime of A, x minus A, that power series, and then the values of the function 1, derivative A is 0, right, and then 2. By the way, the whole thing that we calculate is this, so that's why we don't write divide by 2 factorial, we already did. Just the whole coefficient here. One minus 2x plus 2x squared minus 4/3 x cubed. Like I said, make sure you know how to do this because you will see this a lot. Right. The next one actually very convenient because we just couldn't do that. Have to go over again. Right. Next, approximate given this using Taylor polynomial with n equal to 3. So Taylor polynomial of order 3, we just say P3 of x. And then compute the absolute error. And what we do is, for the function, oh, sorry, don't know the function. E to 0.09. Right. So that's all we know. What we need to write is first, what is the function? By the way, before we answer that question, 0.09, let that be x. So we have e to the x as a function. And also, where do we choose the center? Usually we choose something that is very easy to evaluate. And for e to the x, the only nice values it has is e to the 0 power is equal to 1. So in this case, we choose the center at 0. Right. And I wish we just have something to stamp that, because I don't want just have to draw that every single time. But it's good to build repetition. Because after all, like I said, this is the last thing I hope you forget about this section, this chapter. It's up to order 3, so we need 3 of them. Right. The k derivative of x k derivative at a, where a is 0, and that k derivative at a divided by a factorial, k factorial. Right, so now this one easy. The function is e to the x, derivative is just e to the x on the way, so we don't have to do much. Yeah. Derivative of e to the x is e to the x. Now a equal to 0 and all of them equal to 1, because they're the same thing. E to 0 power is 1. Right, it's not that bad. Now we still need to divide by factorial of k. 0 factorial is 1. One divided by 1 is 1. 1 over 1 factorial. 1 over 2 factorial. 1 over 3 factorial. And then put it in here. Right now, since a is equal to 0, I don't have to write x minus 0. I just write x. So P3 of x is 1 plus 1 times x plus 1/2 times x squared plus 1/6 times x cubed. And then we evaluate this at x equal to 0.09. Right, 0.09 store to x, 1 plus x plus 1/2 x squared plus 1 over 6 x cubed. That round to 7 decimal places. What? Let's write the answer first. 1.09 41715. 1.09 41715. How many decimal places? 1, 2, 3, 4, 5, 6, 7. Right, we have 7. Good. Absolute errors. So we're going to take the actual values, subtract this, and absolute values, that is the absolute error. So a to the 0.09, subtract, just go there, copy and paste. Of course not like that. And get down, subtract, right, like that. And we have used scientific notation and use the answer part from this route to decimal places as necessary. So 2 decimal places, 2.7, right, 2.78, and then use this times 10 to the -6. Right, yeah, have to use that times. Right, use same thing, but this time we have cosine. $21. Right, now approximate using P3. And find the absolute error. And cosine of 0.34. So without any assumption, this have to be in radian because we don't have degrees. Right. So I'm just going to make a table. Right, so K, this one we use P3 again, so 0, 1, 2, 3, K order derivative of X, K order derivative of A, yeah, of course, in this case, what's A, and then that, K factorial, right, so we don't have anything. So first, for this one, if we let X equal to 0.34, then we have the function. And once we have the function, we can choose something that is close to a nice value. So I could choose center as 0. Right. Right. So the function is cosine of x. We have cosine of 0 is 1 divided by 0 factorial is 1. Right, let's just take derivative. Negative sine x. Derivative again. Negative cosine x. Derivative again. Negative sine x, which is sine x. Right. Yeah, once we get used to it, we can just do this table at any way we want to. A equal to 0, sine 0 is 0. Cosine of 0 is 1. And then sine of 0, 0. So we only have those two terms. Since this is center at 0, this is P3. So have 1 and then 0, x minus 0, a0, center is 0. Right. The whole thing here, don't mind that. That's negative 1/2. X minus 0 square. And then we have 0, x minus 0 cubed. That one cancel, that one cancel. Just have that. And at x equal to 0.34, P3 of that. .34 down to x. 1 minus 1 over 2 is 0.5 x squared. 6 decimal places, really. Okay. And then we're going to take cosine the actual values. And then absolute error. The actual values. Minus right. 2 decimal places, 5.54 times 10 to the negative 4. 5. Right. Next, determine the radius of convergence. That's the endpoint if we need to. Right. So this will find the radius of convergence. Right, so we have the series. You see, sometimes it's not important to write the index. They're just going to ignore it. And we just write like this. And when we do this, the way we do the testing is using the ratio test. Most of this problem, we use the ratio test to find the radius of convergence or the interval of convergence. We use the ratio test. Let's see how many of this do we have. A lot. I don't have to do the last 3 because that's just a table. Right. Ratio test. H of k equal to 10kx to the k power. Actually, this one root test is not going to be bad either. But ratio test, let's try that. Just do that. By the way, on this one, you will see, they don't have the ratio. That's what I'm trying to say. Right. Notice that the only thing that changes is k. So instead of k, we have k plus 1. And then x, all of which raised to the power of k plus 1 over 10kx to the k. Right. Now the 10 raised to that power the k plus 1 raised to the k plus 1 x k plus 1, and then we have 10 to the k, k to the k, x to the k. Right. That of course the ratio test. Now trying to simplify this. Hope I don't run out of paper. Right. Now we split. Ten to the k, 10. K plus 1 to the k, k plus 1. X to the k, x to the first, or just x. Over 10 to the k, k to the k, and x to the k. That cancel out. That cancel out. And that not quite cancel out. Still have k plus 1 and still have x. Right, let's try to. First of all, the absolute values is not necessary since all of these are positive. I put this together. K plus 1 to k over k factorial. And then we're left with 10 k plus 1 x. Yeah, this one not quite cancel. Why do I write k factorial? Right. And I will bring both of them under the power of k. I take that back. I still need absolute values because x can be negative, so that's why we need absolute values. Sorry about that. Right, did we do this one before? Oh, here, k over k plus 1. Actually, we did not do that. Yeah, here. Limit of when k go to infinity of k plus 1 over k to the k power. All of that equal to e. That's equal to e. So the proper way to write this is, we cannot just say e there, but the proper way to do this is we're going to split. We say we have k plus 1 over k to the k power times the limit of the remaining. Right. This one is equal to e. Now, that's the big problem. Limit of this, where we put infinity in here, infinity times x is equal to infinity unless x equal to 0, right? Let's say this limit equal to infinity unless x equal to 0, in which case this would be equal to 0. Only if x is equal to 0. If x equals something else, it will equal to infinity because absolute value, so it's going to be positive infinity if x not equal to 0. So because of this, and we have the ratio test. Let me just write this real quick. The ratio test is convergent. Ratio test is convergent only if absolute values are less than 1. In this case, 0 is less than 1. So the series is convergent. Only for x equal to 0. So in that case, because it only had one point, then the radius of convergence is 0. Or we say radius of convergence and the interval convergence it's just 0, just 1 point. The interval convergence is just 1 point. Right. The next one is going to be the long one. Determine the radius of convergence and the interval convergence for that series, and that is -1 to the k, so alternating series. 23. So radius of convergence and interval of convergence. So it's going to be a long problem. Not that difficult. It's just long. Actually, it might not be long, but yeah, maybe this one. Who knows? We'll see. Right. Always find radius convergence, interval convergence. Try the ratio test, because in the ratio test we have the absolute values, and that gives us the radius nicely. Right, ratio test. Right. -1 to the k plus 1, x to the k plus 1, 2 to the k plus 1. Okay. Over -1 to the k, x to the k, 2 to the k. Multiply reciprocal. This 1 to the k plus 1 is -1 to the k times -1. Then x to the k times x. Two to the k times 2. Okay, sorry. Multiply reciprocal. So that -1 is on the top, so we move to the bottom. 2 to the k on top. Right, simplifying. 2 to the k, x to the k, negative 1 to the k. So what's left? Negative x over 2. Everything cancels out is that. So absolute of negative is the same thing as absolute values without that negative. If we want convergence, this will be less than 1 for it to be convergent. Less than 1 for the series to converge. So, by the way, we don't need to write the absolute values of 2. So we're just going to say like this. Multiply 2 on both sides. X less than 2. So with that, we can actually write like x minus 0. So the center at 0 and the radius of convergence is 2. So we know that is 2. Right. Next, find the interval of convergence. Now this is a lot more work. So radius convergence is 2. By the way, if we're going to solve for it, we're going to draw the line, and I think this is always much better to visualize this. Taking the problem this way. It's centered at 0. The radius less than 2, meaning 2 up, 2 to the left, and 2 on the right. Give us negative 2 to 2. So x is between negative 2 to 2. Right. So we know that is convergent on this one, yes. But what happened at 2 and what happened at negative 2? So we have to check for boundaries. Usually this will not be as bad. It's just a little bit long. Boundary will be when x equal to negative 2, and then when x equal to 2. And we just put negative 2 back into the original problem, which is that. And so we have absolute values of negative 1 to the k. Now x is negative 2. So that's the series we have. Now, we can bring both of them under k, all of them under k. Negative 1 times negative 2 over 2. K will be over all powers. Negative 1 times negative 2 is 2 over 2 is 1. So we just have 1 to the k. And of course this one definitely diverge. It's silly. Just a series of 1. Actually, if we just going to write down 1 plus 1 plus 1 plus 1, which is equal to infinity. So that's why this is diverge. It is divergent. Now we'll test for when x equal to positive 2. Right. So this is the series, Now we're going to put 2 in it. I put 2 in for k, 2 in for that x, sorry, 2 for x. This one cancel out. Yeah, and we have that. So basically this we just have minus 1 plus 1 minus 1 plus 1. We don't know what is the end term is, so this is divergent. Or we just say this the divergent test. If the k term, when k approach to infinity and h of k not equal to 0, which we have 1 in this case, when k go to infinity it goes to 1, and when k go to infinity we don't even know what this one go to. It could be 1, could be -1, but we don't know. Either case it is not going to be 0, so it's divergent. Yeah, so this doesn't go to 0 and this doesn't go to 0, so this is divergence. Alright, now let's go back to our problem. We have convergence within this, divergent at 2, so it doesn't work at 2, and it doesn't work at -2. So the answer for the interval convergence is just between -2 and 2. There is not including the 2. Wait, what? Interval notation. Alright, I have to read the question. Right, parentheses. By the way, my MATLAB should take that answer as well. I just don't know. Right. And it said when it asks for interval convergence, I should actually put that in the interval notation instead. But we have that. Right. Next, also ask for radius and interval convergence. And we have the series k squared x plus 3 to the 2k over k factorial. So when we write like this, look like the center at -3. Right. So ratio test. a of k plus 1, so I have k plus 1 square x plus 3 2 k plus 1 k plus 1 factorial k square x plus 3 to the 2k k factorial. And multiply the reciprocal. I will actually distribute the power 2 to the k plus 2. Reciprocal k factorial k square x plus 3 to the 2k. I don't remember I signed this one. Go to infinity, sorry. Right, k plus 1 infinity, k plus 1 square, sorry. Cannot really do anything with it. This one though, plus 2, so we can say x plus 3 to 2k, then x plus 3 square. So 2k plus 2, when we multiply, add the powers. K plus 1 k factorial k factorial k square x plus 3 to the 2k. Actually I did meant to assign this one. Cancel out, cancel out. It looks like something's off here. So I have k plus 1, k plus 1. Cancel one of them actually. Right, what's left? K plus 1 over k square. Oh, now I do remember assign this one. Now, right? By the way, we have the squares. We don't really need the absolute values. So what I do is I'm going to split for the limit for that term first, and then the limit of the others. Now, notice that since this one equal to 0, because the bottom is bigger power, so let's actually just write that out. Highest ranking on the top, ranking the bottom, k square. So finite over infinity, so that is 0. Now, so if this 0, this doesn't matter because 0 times anything is equal to 0 unless that equal to infinity. So I will write like this. If this is not equal to infinity, then the whole thing is equal to 0. If it is equal to infinity, then we don't know that. It's indeterminate. However, if it is equal to 0, then the radius equal to 0 less than 1. So r equal to 0, which is less than 1. If x plus 3 does not go to infinity, and because when r less than 1, the series is convergent. So in that case, it is convergent if x is less than infinity and greater than negative infinity. So pretty much as long as it is finite, it's convergent if x is finite. And this is where we mean when we write that if x is finite between negative infinity and infinity. So the radius is infinity. Of course, you can just click infinity here, but if you want to type it, it's backslash inf. And interval convergence on real numbers, inf. 25. Find interval convergence of the series. This one only asks for the interval. Right. So we have a lot of scenarios in this case about interval and radius of convergence. If it is equal to infinity, we don't check the boundary. If it is equal to a number, if it is equal to 0, we don't check the boundary either. So if the radius is equal to something in between, then we have to check the boundary. Like this one. Look like this one, we need to check the boundary. Alright, we'll see. First, ratio test. So ratio test. And then we use n instead of k. So again, this problem from different book. But for sometimes switching the index, and then we actually have a better perspective about the problem. Sometimes just change the variables in the formulas. I mean, change the letter just to get a better perspective. Right, so I'm going to put n plus 1 in here instead of n. So I have x minus 6 to n plus 1 over 1 plus 4 n plus 1. And then the bottom just the same thing. Forgot to the n. Right, multiply reciprocal. This is 4 times n, and 4 times 1 is 4, so 4n plus 5. Multiply reciprocal. 1 plus 4n on the top, x minus 6 to the n. Right, let's simplify. Oh, before we simplify, let's rewrite this as x minus 6 to the n, x minus 6, 1 plus 4n, 4n plus 5, x minus 6. Let's simplify. Now, I'll put these two together. And then what's left is just x minus 6. Again, n is positive, so we really don't need to put absolute values here. And furthermore, because there's no n in here, that's why we can put that. Right. Let's just write that as an expression like this. Right? Just scrambling out. And then finally, because this one has no n in it, it doesn't have any n, I'll just take it outside. Just like when it is in the integral, if we have a constant, we just take it outside. In this case, we don't have a constant, but it's still independent of n. Doesn't matter what n goes. X minus 6 doesn't affect by it. Then we find the limit. Highest power, or highest ranking, x minus 6, 4n, n go to infinity. That cancel out. And limit of 1, which is 1. So that is R. So R equal to absolute value of x minus 6. Ratio test say this is less than 1 for the series to converge. So when we write like this, 1 is the radius of convergence. And now we have the center at 6. The radius is 1 on the left and 1 on the right. 6 plus 1 is 7. 6 minus 1 is 5. So we know that's going to be between 5 and 7. Don't just go ahead and answer B, because we do have the equal sign. We're not sure where that come from. Yeah. We don't know where that negative come from, but it's from 5 to 7. That is for sure. Right. Now we don't. If the radius is equal to 1, if it is not 0 or infinity, we need to check for boundaries. When x equal to 5, right, let's put 5 into the series. Wow, that is the series. Put 5 into it. Or we have the problem, so this is the series. So at -1, this is the alternating series. We can check the boxes. Is h of n non-increasing, and does the limit equal to 0? And it is easy to show that as n increases, the whole thing at the bottom increases. The top is finite though. Finite divided by something getting bigger, we have the smaller quotient. So yes, that is non-increasing. And is the limit go to 0? That also true, because if n go to infinity, finite divided by infinity is 0. So yes, both of them check. So yes. So then we go back to our problem, and we're going to add the equal sign there, because 5 works. 5, it is convergence. Now we check for x equal to -5. Sorry, I don't know where's that come from, but I mean 7. Seven minus 6 is 1. And we have 1 over 1 plus 4n. And this series is convergent or divergent. Right, we did this. I think if you go back to the first problem we did in this review, if we compare to that, take the one with the higher ranking, or we can compare to the one without the constant. And this is the P series, where P equal to 1, and that is divergence. So if this is divergent, so is that, because that's why we compare them, right? So for 5 it works, for 7 it doesn't. So this one only go from 5 including the 5 to 7, but does not include the 7. This review is longer than I anticipated. Right. Next one, actually this won't be very short. Use the geometric series to find a power series representation for that. So this is 26. We have 1 over 1 minus x is equal to the geometric series x to the k for absolute values of x less than 1. Now find the power series for this. No, not power series for that. We want the power series. Actually, this one only takes about 2 minutes max. So first of all, I'm going to write g of x, move the x to the 7 on the way back, because I need to have that term. And then we have this, which I will substitute into that part. So we have k equal to 0 to infinity, x to the k, all of that times x to the 7. And with that we can multiply the x to the 7 inside. X to the k, x to the 7. So x to the k plus 7. So we try to visualize the power series as much as possible. Right, the interval convergence. This we take advantage of that. Whatever the interval convergent of f of x is also interval convergent of g of x. So it is absolute value of x less than 1, absolute value of x less than 1. So we will say between -1 and 1. Right. 26. Pretty much we do the same thing though. Somehow we have to go back to that. Not exactly, but you get the idea. So first, let's move the 6 in the front. Why not? That's good, right? Now we just need to turn that into 1. How to do that? How about multiply 1 over 6 on the top, 1 over 6 at the bottom. Actually, that's a much longer way to do, but anyway, 6, 1 over 6, 1 6 times 6 is 1, times that is x over 6. Right, now take the 1 6 in front. that gives us 1, right? That cancels out. So we just have this. So have 1 on top, 1 from the beginning, which is good. But it is minus though. So in that case, we have to write 1 minus x over 6. And according to that, if we substitute this into x here and x here, we have this equal to the summation. Now we substitute this in for x. And that's what we have. And the interval convergence. Now it's different. Whatever that is. So we say interval convergence. Oh, I thought we not done yet. It's quite a lot of work here. We're going to have negative x over 6 have to be less than 1. Yeah, remember when we substitute that for x, we have to substitute for this x as well. Right, absolute value of negative doesn't matter though, just drop that. And if we're going to draw it, this is the same as x minus 0. So pretty much absolute value of x less than 1, meaning it is between negative 1 and 1. Yeah, 1 to the left, 1 to the right. So negative 1 to 1, and we know that we're not going to include the 1. So parentheses both ways. I don't know what I do with the 6. Sorry, absolute value of x over 6 and multiply 6 on that side. So this should be 6. Sorry. Oh, come on. Right. I will not do the next problem. Oh, this is, wait, the last one I did was 27. This one is 28. Right, I'm not going to do this. Because if you're going to take the derivative of this, it's very complicated. So the question asks for find the Maclaurin series. Maclaurin series. A Maclaurin series is where center is 0. Right. Find that series for the first. Four non-zero terms. By the way, if you're going to do it like that, that would be extremely complicated. Unless we use this, sine of 2x is equal to sine x cosine x, double angle. So sine x cosine x is 1 over 2 sine of 2x. Be a lot more easy to do. And if you can construct a table center 0 for that function. That should be easy. Complicated, I mean. I didn't check this. I just gave that. The next one, the same thing. Yeah, this one just make a table. Find the first 4 terms, take derivative, and so I'm just going to let you do that. And that's one. Find the first 4 terms of Taylor series center at A. I'm not going to do that one either, you just make a table. But here's note that e to the x, and this is a equal to ln of 9. So e to the ln of 9, that cancel out is equal to 9. Just give you this hint. The rest you have to construct the table, and I just put it as the, by the table I mean this kind of table. Yeah. I think you need some practice on that. So anyway, I'm going to stop here because that's almost 3.5 hours already. So I hope you find this video helpful. As always, thank you for watching.